Okay, all right. Well, good afternoon, everybody. Um, so today what we're going to do is we're going to talk about measures of central tendency and measures of dispersion. But just a quick reminder, um, your homework in your classroom, if you click on this homework tabs here, your first homework is due next Thursday. I accept homeworks until Thursday at 11:59 p.m. Eastern time. Um, so just make sure you have it in by then. All you're going to do is you're going to click on the link. You're going to browse, attach your homework file, and you're going to hit submit. That's all you're going to do. Has anybody, I know it seems like a few people have tried the homework. Has anybody else given the homework a shot? Yeah, good. I hope it doesn't take too long for you all. Yeah, the first homework I think is the easiest of all the homeworks. I'll show you talk about how to do all this stuff in class today. Right here, this is the only stuff we haven't talked about before, but every other problem we've done in class before. Okay. So I'll take any last minute questions on the homework next class on Thursday because it won't be due by then, okay? Just to let you know, I also increased the number of submissions to this to two submissions. So if you make a mistake with your first submission and catch it before the deadline, you can do a second submission. I've also in the classroom created a new tab called recorded lectures. I just thought it'd be easier to put all the recorded lectures in one place. So after class, I'll post the recorded lecture here. It's going to take me a little bit of time to get this one posted. Oh yeah, go on ahead with your question. You can turn your mic on if you're comfortable with that.
Okay, so Professor, also when you were showing the homework, the question with the next graph, I'm sorry, I don't have it pulled up.
That's okay, I'll pull it up. Here?
Yeah, that one. Yeah, that graph is not showing on my like when you put it as a doc, on both PDF and doc, they're not pulling up there.
On your computer, they're not showing up?
Yeah, just that question, like that graph right there, the miles per gallon graph, it's not showing up on any one of mine.
That's weird. It's probably. Do you have a Mac?
Yeah.
Okay, you're a Mac person. Grr. Okay. Yeah, try downloading the file again. If not, what you should do real quick is take a quick print screen. Like, do you have a print screen button on your Mac?
Let me see. I'll be honest with you, this is my friend's computer. He's letting me use it for the semester, so I'll just take a picture of it with my phone.
Okay, do that real quick. I'll leave it up there for another couple of seconds. Yeah, it's a technology issue on your end. I don't think, because looking in the chat, a lot of people have Macs.
Dennis I tried the Command P.
Okay.
No, it didn't work, but it's all right. He has the older Mac, so I'm still learning myself.
I get you. While I am an iPhone user, I am anti-Mac. I am anti the Macs.
I heard.
Which is funny because my wife is a big Mac person. So we're a house divided, as they say. Yeah, Dennis, if you, not Dennis, whoever was asking the question, if you shoot me an email, right after class, I'll email you the PDF and see if that helps. That might help.
Okay, sounds good.
I'll just shoot me that email and I'll take care of it after class for you. All right. Any other questions? Anybody else? All right. Here's another question. How many people have their graphing calculator with them today? Okay, we're going to use it a little bit today. I just want to say a few things. I have a TI-84 emulator and a TI-83 emulator on my computer. So during class, whenever we're going to use a calculator, I'll load up the TI-84. And now, if you have a TI-83, most of the commands will be exactly the same on the TI-84. okay? On the few instances when we don't have, or when the commands are different to install, or different, not to install, different to use, I'll load up my TI-83 emulator. I don't, unfortunately with the TI-30XS, I'm not gonna load up. You need a TI-83 or higher for this class. So whenever I only show the TI-84, it'll be because the commands are the same exact options in your TI-83 calculator. If you just Google TI calculator emulators, you should be able to download them. Some of them cost money. I'll be honest with you, as a professor, I got the department that gave everybody a TI emulator for free. I'm sorry, I don't know how much they cost for you. I hate to say this on the recording, but I'm not saying you should do this, but if you can find a way to download it, you know. I'm not fancy with that type of stuff, but you could do that too. They're also pretty cheap if you buy it off eBay. You can get a used one for like 30 bucks or something, or Amazon. So whenever I have the TI-84 loaded up, if you have a TI-83, it's just the same commands. When the commands are different, I'll load up both so you can see, so you don't feel left behind if you have a TI-83. All right, does that sound okay, everybody?
Yes, Professor, I have a question.
Mm-hmm.
When is the next test on what we're doing these next classes and last week?
Yeah, let me show you. So if you look at our outline for the course, our first test it's going to come quick, actually. It's Tuesday, 9/22 is our first exam. So we've got this week and then next week, and it's going to cover all these topics here. Okay, so we're right here today, measures of central tendency and dispersion. Thursday, we're going to do box plots and scatter plots. And then the week after that, we're going to do correlation and regression. And then we'll have our first exam Tuesday the 22nd.
Okay, thank you.
Yeah. We'll also have a review day on Thursday, and I'll post a sample exam for you so you can see what it's like. Okay. Also, you're going to have a homework due the same day as the exam day. I designed the homeworks to be, honestly, like exam prep for you. So generally, I'll be honest with you, if you do the homework and spend a lot of time on that homework number 2, you will do just fine on the exam. Okay? Any other questions? All right, so today, Today we are going to learn about 2 main topics today. We're going to learn about, so today is basically an introduction to numerical measures for a data set. All right, and I will be honest with you up front a little bit. Some of the stuff today is a little dry. You know, it's like, what's an average? What's a median? What's a range? So don't get too discouraged. Just kind of stick with it. I promise you everything does get a lot more interesting, especially starting next week. I find the class really takes a turn and it becomes really, really interesting. All right, but there's 2 topics we're going to cover today. We're going to cover measures of central tendency. And we're going to cover measures of dispersion. All right, so probably before the break, we'll get to cover this, and then after the break, we'll cover this. All right, so what you're going to notice today too is I'm going to show you how to do everything by hand. And then eventually what I'll do is I'll show you how to use your calculator with it. Okay, so it's important to know how to do stuff by hand. But then whenever we can use technology to make this class easier, we're going to. Okay, so what are measures of central tendency? Okay, so we're going to look at 3 different concepts of how we describe a typical data element. So there's 3 concepts we're going to learn in class today: the mean, the median, and the mode. So when you hear the mean, what is that synonymous with? What word do you think of when you hear the mean?
Average.
Yeah. So the mean is an average of some type. How about the median? What do you think of with that? Yep, you guys got it in the chat. It's the middle data value. And the mode is going to be, yep, thanks in the chat. It's the most, the value that occurs the most, mean, median, and mode. Now, these are all, I'll be honest with you, incredibly simple to find. So I'm going to spend a little bit of time talking about notation because in this class, notation is incredibly important. So for a mean, there's two different types of means, okay? Okay, there's what's called a population mean, which we denote with this Greek letter, and this is the Greek letter mu. And there's what's called a sample mean, which looks like this. Okay, it looks like an X with a bar over it, and it's literally called X bar. All right, a population mean is a parameter. Okay, that means it comes from a population. X bar is a sample mean, it comes from a sample. So it's a statistic, okay? All right, now how you take an average, incredibly easy, right? Like if we wanted to calculate, there's 24 of us on this call right now. If we wanted to calculate how many, the average amount of sleep and in terms of hours we got last night, we'd ask everybody how many hours they got. We'd sum all those up and then just divide by how many of us there are in the class. That's it. Like I think we've all taken an average before. You know, like how many people on the call got more than 8 hours of sleep last night? Just out of curiosity. Anybody get more than 8 hours last night? Oh, it must be nice. Must be nice. Yes, what's sleep? Wait till you all have a newborn, okay? And then you'll understand sleepless nights. That's why I'm on my like 10th cup of coffee today. Okay. So here's the notation for this. Okay. If x sub 1 comma x sub 2 comma x sub capital N, and remember capital N is the population size. So what this subscripted values are, it's the first value in the data set, the second value in the data set, all the way to the nth value in the data set. Is a variable of population, then the population mean is given as, so mu, you just sum up the data. Okay, so you take the first value plus second value, and then you just divide by n or divide by how many there are. Okay, so a little bit shorthand notation. Does anybody know what this notation means in mathematics? It's actually the capital Greek letter sigma. So what this is this is a summation sign. So this is how you write this shorthand. Instead of saying x1 plus x2, this just means sum up each x sub I. So the x sub I means the individual x values. So sum up the x values, divide by how many there are. So whenever you see this, it just means sum up the x's. That's it. All right. How you calculate an average for a sample is exactly the same, just the notation is different. That's it. So if x sub 1, x sub 2, x sub all the way to lowercase n are the lowercase n observations of a variable from a sample. So lowercase n, just remember, means the sample size. Then the sample mean, x bar, okay, is given as just sum up the x values. Here, just divide by how many there are. That's it. So it's the sum of the individual x values divided by how many there are. All right, taking an average is incredibly simple. Just the notation is really, really important. So Greek letters, yes, there is really a formula. Greek letters are parameters. This type of notation, other notation is statistics. So I'm not going to spend time like actually working through problems in class. I just want to show you when you would use a Greek letter versus when you would use a statistic, okay? Here's an example of a population mean, okay? So there's 3 countries in North America, right? So capital N is equal to 3. Is your friend, Abigail, is your friend in our class? Sorry, someone just messaged me privately.
Yes, yes, please, Professor. Yes, please.
Just have them join via the Blackboard classroom. Just follow the link in the classroom.
She said, please, she said she can't have access to the link to join from Blackboard. So I should ask you the password. That was why I sent you the message.
Okay.
Thank you.
Professor, can you please go back to the previous slide for a second?
Yeah. Here's the password. It's 8Y4720. Okay. So can you tell your friend that? Okay. Go back to this slide you said?
Yes, just for a second.
Yep. And don't stress too much. I am going to post this, my scribble notes to the classroom too after class. Is it okay for me to go to the next slide?
Professor, I just have.
Yes.
Yeah, whoever had the question, go ahead.
By statistic, do you mean like, it's just, I get confused. Do you mean like the whole population by that?
Nope.
Or?
Okay. So what we call parameters, okay, these thing called parameters. So whenever you calculate a value, all right, from a population, okay, it is referred to as a parameter. Whenever you calculate anything from a sample, that's referred to as a statistic.
Oh, okay, thank you. Now I understand. Thank you.
Yeah, no problem, no problem. It's terminology and definitions is the hardest part of the initial stuff. Like taking an average is easy, but understanding the intricacies of notation and definitions is the hardest part. So that's okay. Okay. All right, so to go back here, this is an example of a population mean. So there's 3 countries in North America. So this data set here of Canada, Mexico, and United States, okay, is a population set of data because it's all the possible values. If you wanted to figure out what their average land area is, okay, here's their land areas in kilometers squared. All you would do is you'd sum up all the values, a little extra 4 here. Sum up all the possible values, divide by 3, and that would be what the population mean would be. And just in the forums there, yes, I agree that you print the slides beforehand and scribble the notes. It definitely just helps with learning instead of just sitting here for 2 hours and watching me. Yeah, like having writing this stuff down makes it easier. And I promise actually as the lessons go on, I know I'm getting on a bunch of tangents here, but as the lessons go on, there will be more of us working the problems together instead of me just reading off slides, okay? Even a little bit later today, we'll do that, all right? So it's gonna get better. You know, like someone posted in the forums, the reality of remote learning, I'm gonna try to make it better. We'll get there. All right, back onto the class, off the tangent. So whenever you have all the possible data values, that's a parameter, and that gets the Greek letter. Here's an example of a sample mean, okay? Suppose 10 people are asked how many hours of TV they watched last night. Okay, so here are the responses in hours: 1 hour, 2 hour, half an hour, 0 hours, 4 hours, so on. What does the sample mean? Well, this is obviously just a sample, okay, where n is equal to 10. Like, did more than 10 people in the United States watch television last night? Yeah, like for sure more than 10 people watch television. So this is just a sample. It's not a list of all the possible values that you could have. So this, because it comes from a sample, this is a statistic. Okay, and gets this X bar notation. So how you take an average, just sum up all the possible values. Then there were 10 people, so all these sum up to 14. 14 divided by 10, you'd say the average, the sample mean was 1.4 hours of TV last night. Okay? Only hard part here is the notation. That's it. All right, the median. Okay, so now how you find the median, which is the middle data value. Okay, I want to stress this. No special notation for the median. And I'm just going to say for now. We're going to talk next class about a designate for the median. But for right now, we're not going to distinguish between a sample and a population. Okay, we're just going to say, oh, here's your data set. This is the median value of the data set. Okay, so none of this mu and X bar stuff for the median, okay? So I use what's called the n+1 divided by 2 position to find the median, okay? And a little bit of a typo here. All right, looks for the median of a day set when they are sorted. I'm always gonna sort it lowest to highest, okay? So there's two cases here, okay? If the number of observations is odd, how you tackle it is different if the number of observations is even, okay? So if the number of observations is odd, this is the easy method, or the easy type of problem, okay? If the number of observations is even, it's still easy to find it, just need an extra step. Okay. All right, so if the number of observations is odd, then the median is the data value that is exactly in the middle of the data set. Okay, that is, the median is the observation that falls in this n+1 divided by 2 position. All right, so let me do an example of this first. Okay, so how you do this by hand. All right, so here's an observation or an example. Robert, he hits 11 golf balls at this place called Grisby Driving Range, okay? So he records the distance of his drives measured in yards. Okay, so I already put the data set from lowest to highest, okay? You can see he had a drive that went 50 yards, one that went 140, and maybe just Robert isn't great at golf here. Okay, if you know anything about golf, those aren't really great drives, but okay, so I want to find the median distance here. So since the number of observations is 11, it's odd. Okay, so when you have an ordered data set, all it is you go to position n+1 divided by 2. So the median occurs in position n+1 divided by 2. Well, 11 plus 1, because remember, n is the sample size, plus 1 divided by 2. What's 12 divided by 2 get you? Yeah, okay, so what it says is in position 6 of ordered data is where the median is. So here's position 1, 2, 3, 4, 5. Here's position 6. This is the median. Okay, the median is equal to 85 here. And you can see that makes sense, right? Like if you count, there's 5 values on either side of the median here. So that is the data value that falls exactly in the middle of the data set. Okay. So this n plus 1 divided by 2 position will always work for finding the median by hand. Okay, going
Professor, I have a
back.
question. Sorry.
That's okay. You can interrupt me whenever you want.
So today I was looking to help me with the homework on the slides that you have written, like the ones that you made comments on.
Yeah.
And it's not there anymore. So
So
after you're done, are you able to like?
yep. I don't know if you missed this. Let me just to go back.
Sorry, I didn't.
That's okay. That's okay. Remote learning, right? We're all
Yeah.
getting used to this. So what I said was I actually created a new tab called Recorded Lectures.
Okay.
And you can see I put them there.
Okay, even the ones that you have like marks on?
Yep, they're all right here. The data, see how it says attached files?
Okay, okay.
Yep, they're all
Thank
there.
you.
They're all there. Yep, I got you. Don't worry about it. I just thought it would be easier to put the recorded lectures there, all in one place. And I'll do that right after this class here, okay? Just takes me a couple hours to do it. Right.
Okay, thank you.
Yeah, you're more than welcome. Okay, going back, where was I? Okay, so now what happens if the number of observations is even, right? It's still easy how to do it, it just requires an extra step. All right, then the median is the mean of the two middle observations, okay? So the median is the mean of the middle two. So you have to find the middle two observations. So first find middle two. All right, that is the median is the mean of the values on either side of the observation that lies in the n plus 1 divided by 2 position. Okay, so we're still going to use this n plus 1 divided by 2. Okay, we're just going to now use it to find the middle two observations. All right, so let me show you that. So let's go back to kind of the same data set. Robert hits these 12 golf balls at Grisby driving range. Here are his recorded distances. Okay, so again, n, that's our sample size. It's the number of balls Robert hit. So position n plus 1 divided by 2. You get 12 plus 1 divided by 2. What's 13 divided by 2? I think it should be 6.5. Yeah. Okay. So what this is saying is the median occurs in position 6.5. Okay. Here's position 1, 2, 3, 4, 5. Hey, here's position 6. Here's position 7. So the median must be right here. Okay, but notice how like there's no value there. So what you do is you estimate it or find it by taking the average of these two. So then the median is equal to 85 plus 95 divided by 2. I think that gets you 180 divided by 2. And the median here is 90. Okay, so if there's an even number of values, you just find the middle two and take the average of them. All right, pretty straightforward. It's just an extra step, just an extra step. Okay. So a little bit cleaner version here you can see in the slides. All right, now let's just talk about the mode next. And the mode is the observation that occurs the most. All right, so one great thing about the mode is it can work for qualitative data. Like for example, if you have this place called Hillwood Cafe, and here are 20 opinions of Hillwood Cafe, the most common response here, okay, is that the mode is fair. If you have numerical data, something like this, for example, data set that looks like this, 7, 7, 8, 8, 8, 9, 10, 11, and 13. What would you say the mode is here? Yep. Okay, but what if you have a data set that looks like this? You have the values 5, 6, 7, 12, 15, 20, and 25. There's actually 2 right answers here. You can either say there is no mode because there's no value occurs more than once, or actually by the definition, you could say they're all the mode. Yep, you have it right, Tora. Yep, because they all occur the most, they all occur one time. So it's either none or all. It's fine. It's totally fine. All right, there's not much more to say about the mode. It's very, very straightforward, pretty easy to comprehend. Okay, before we go into break, I just want to get through this because I'll take a break in about 17 minutes, around 1:50 for 10 minutes. I just want to talk now about a slightly different measure of central tendency called the weighted mean. All right, so this is still a measure of central tendency. And so we've all heard about the mean, median, mode, but maybe you've never heard of the weighted mean. So I actually want to do 2 examples of the weighted mean. I'll talk about what the formula is. I'll walk you through one with the slides, and then we'll do one by hand together. Okay, so you have this concept of the weighted mean, and it occurs when you have some observations you wish to place more importance on than others. Okay, what I mean by that is you want to weight some data values more. Okay, like if you look at a data set, oh, this value is obviously more important, so I want to put more weight on it than others. So to do this, you need to introduce what's called a weighting variable, okay? And a weighting variable indicates the importance you wish to place on some given observation. Now, when you're going to pick weighting variables, very, very rarely do you ever just say, oh, I'm going to weight this. This is the most important value, so I'll weight this value as 1. I'll weight this value as 2, so on and so on. It's not like that, okay? The problem will dictate the weighting variable. Okay, so you're going to see 2 different examples where how you pick the weighting variable is completely different. Okay, so we denote our original variable by x sub I. That's what we're originally interested in. And we denote a new variable, the weighting variable called w sub I. So this is going to be a new variable. Okay. All right, let me give you an example of this. And I think this illustrates why you need the weighting, this concept of a weighted mean. And actually, I'm sorry, before I do that, let me give you the formula. Sorry, I'm getting ahead of myself here. Okay, so the formula for the weighted mean is as follows. So we just call it the weighted mean, or x bar w. There is no other notation for it. There is no difference between a population and a sample one. This is just denoted as the weighted mean, and that's it. Okay, it's kind of like the median. All right, I'm going to write it a little bit backwards from the formula here. So here's what you do. Each value, these are your original data values. They get a corresponding weighting variable. So the first data value has a corresponding weighting variable we call W1. The second value has a corresponding weighting variable called W2, all the way to the last one, like this. So you take your first data value, we'll call it x sub 1, and you multiply it by its corresponding weighting variable W sub 1. I'm just writing it backwards than here, okay? With multiplication, it doesn't matter which order you write it. Then because it's an average, you're gonna sum. You're gonna do some type of sum. You're gonna take the second value times its corresponding weight, and you're gonna keep doing this until you get to the last value in the data set, and you multiplied it by its corresponding weight. And then you're gonna sum all this up. Now you're gonna divide this by not how many observations there are, but the sum of the weights. Okay, so in shorthand notation, all right, we use this summation sign. So it's the sum of the original variables times the weights divided by not how many there are, but the sum of the weights, okay? So actually, the mean we calculated before is a weighted mean in which each weight is equal to 1. Okay, so like the arithmetic mean that we were calculating before, when all the weights are just 1, it just sums up to whatever the sample size is or population size is. So it's actually a weighted mean just with weights 1. Okay, but regardless, this is a little confusing, this formula, like how might and why might we need to use it? Okay, so I came across this data set a while ago, and for some reason I found it incredibly interesting. So this data is a little old, so life expectancy has gotten better in each of these countries, but this was from a government website, and it said, here are the life expectancies in a group of Northern African countries. So there's 7 countries here. There's Algeria, Egypt, Libya, Morocco, Nigeria, Sudan, and Tunisia. I might be mispronouncing that wrong. Anyways, but here's the life expectancy in each of these countries. Okay, who has the highest life expectancy? Looks like Libya, right? So Libya's life expectancy was 73. Who has the lowest life expectancy? This was crazy. Yeah, Nigeria does. Okay, the life expectancy there was 41. And I was shocked by that because I'm getting into my late 30s, almost 40s. So I was like, oh, that's crazy. Okay, if you were to just say, what's the average life expectancy? I'm just going to put LE for life expectancy. All right, you just sum up these 7 values, you'd get 422, you divide by 7, and this would be the mean life expectancy. Okay. All right, so this is what's called an arithmetic mean, or you're just calculating each value has a weight of 1. But now let me give you an extra piece of information here. Okay, and let me show you the population in terms of millions of people in each of these countries. Okay, so here are the populations of each country. Which one has the smallest population? Yeah. Yeah, that's crazy. Smallest population. Okay. And which one has the highest? Yeah. Okay, so we'll look here. If you wanted to calculate a better indication of what the life expectancy is across these Northern African countries, you'd want to take into account that Nigeria has roughly 25 times the population as Libya. Okay, so you want to, this is what I'm saying, you probably want to weight this value more. Okay. And now what you don't want to do is you don't want to say, okay, well, we'll weight this as a 1, we'll weight this one as a 2, whatever. You don't do that. You got to pick some other variable to weight it by. Okay, so for a weighted mean, you need 2 variables. You need x sub I and you need w sub I. So x sub I was my original variable of interest. And what we were originally interested in was life expectancy. Okay, that's what we were originally interested in. So then there's only one other variable here. So what do you think we're going to weight it by? Life expectancy by? Yes, exactly. So here's what we're going to say. Okay, Libya, your life expectancy of 73, we're going to weight with a weight of 5. Okay, that means we're going to weight it by the 5 million people who live there. Nigeria, your value of 41, we're going to weight it by 126. Or by the 126 million people who live there. So this is my x sub I variable. And this is going to be my wi sub variable now. All right, so how we'll do this, okay? Going to go to the next slide and I'll walk you through it. Here's my X sub I variable. Here's my W sub I variable. So weighted mean, it's equal to the sum of each X variable times its corresponding weights divided by the sum of the weights. So what you're going to do is you're going to take each X value and you're going to multiply by its weighting variable. So like 68 times 31 gets me 2108. Then you're going to add to it. You're going to go to the next variable. You're going to take 66 life expectancy in Egypt multiplied by the 70 million people who live there. You get 4620. And you're going to keep doing this, okay? Till you get to 72 times 10 was 720. And then what this tells me here, this tells me to sum them up. So I'm summing up each X value times its corresponding weight. And when you do that, you get 16,627. All right, now how many countries were there in this example here? Yeah, so what you don't want to do is divide this by 7, okay? Because if you divide this by 7, right, you'd get like over 2,000, which makes like no sense for life expectancy. So you divide this by the sum of the weights. So 31 plus 70 plus 5 plus 10 was 302. So when you did this, you end up getting, go back. You end up getting 55.05, as you see down here, okay? And this is, I'll answer your question in the chat in a second. And that's a better mean taking into account the population of each country, okay? So let me ask you a question before I answer Joanna's question. Does that make sense why we would need a weighted mean for this specific example compared to just a normal mean? Yes, absolutely. So to go back and answer the question about are we going to get to practice this? Yep, we're going to do another example right here, right now. And then on homework number 2, you're going to get a chance to practice this. And then I will do another example of this for like when we go through a practice exam for the exam on the 22nd. All right, does that answer your question about when we get to practice this again? Okay. All right, let's do one more example of weighted mean and then we'll take our break. Okay, everybody? All right. So believe it or not, I always like this example. The GPA you get at the end of the semester is actually a weighted mean. Right? So let's calculate a GPA for a student. Okay? And we'll call the student Matt, okay? Even though that looks like an F, okay? God, I'm so bad at writing on this. Okay, so we'll name the student after me. So let me give you some information about the student. Okay, and this is an example where I encourage you to just write this down as I go through it. And this will be a lot how we'll do classes going forward, where I'll do examples like this and we'll work them all together. Anyway, so here are the classes Matt's taking, okay? He's obviously taking statistics. That's a great course, probably the best course you could take. He's taking Calc 1. Okay, that's another good math course. He's taking an English course. Blech. And maybe he's taking an economics course, all right? And on top of that, Matt decides he needs to get in better shape. So he's going to take a running course, okay? Now let me give you the grades Matt's going to get in these classes, okay? What grade do you think Matt's going to get in stats? Absolutely, he's going to get an A. Yep, I agree. Matt gets an A in stats, okay? Probably is going to get an A in calculus, all right? Matt's not the best writer, okay? Ugh. So maybe he gets a C in English. Maybe he gets a B in economics. And Matt is a terrible runner, so maybe he gets a D in running. Ugh. Okay. Your grades are reported on a 4-point scale. So let me give you the corresponding number grades. Okay, on a 4-point scale, an A is worth 4 points, a C is worth 2 points, a B is worth 3 points, and a D is worth 1 point. Okay. If you were to just take the mean here, you'd sum these values up. 4 plus 4 is 8, 10, 13, 14. Matt's taking 5 classes. We would say his GPA is a 2.8. Okay, but do you think that's exactly how they do your GPA in college here? Like, let me ask you this. What's the least important class on this list here? Yeah, running, okay? Although the physical education teachers would probably disagree, okay? Don't tell them. But it's probably the least important in your academic career as compared to maybe stats or English or economics, okay? So we want to weight that somehow. So does anybody know how your GPA is weighted by, what they weight it by? Anybody got a guess? Starts with a C. All right, I'll help you. They actually weight it, yeah, by your credits, okay? Like stats, how many credits is a stat course? How many credits is this class? Yeah, 4. Calc 1 is a 4-credit class. Englishes are generally 3-credit classes. Economics are 3-credit classes. And a running class, phys ed class, is generally 1 credit. So what this means is when we go to calculate your GPA, we're gonna weight like your stats in your Calc 1 class 4 times as much as we weight the running class. Okay, so a weighted mean the formula is the sum of each x value times their corresponding weights divided by the sum of the weights. This was my original variable, x, which means the credits are going to be my w sub I. So doing this by hand, I'm going to put a new column here called x sub I, w sub I. And what you're going to do is you're going to multiply across. Okay, 4 times 4 gets me 16. 4 times 4 gets me 16. 2 times 3 gets me 6. 3 times 3 gets me 9. And 1 times 1 gets me 1. So now what you're going to do here, this tells me to sum this up. So if you were to sum these up, 16 and 16 is 32, 38, 47. This column here sums up to 48. And then you'd have to sum it up by the sum of the weights or the sum of the credits. And it looks like this student, Matt, is taking 15 credits. So the GPA that would actually be reported to the student, if you were to take this 48 divided by 15, that would be the GPA the student would get, which is a lot better than the 2.8. So I actually encourage you as, at the end of the semester, like when you get your grade report, you should see if they do it right. Okay, I used to do this as an undergrad. I'd always calculate my GPA, make sure my undergrad institution did it right. And every time they wouldn't, I'd be like, oh, dang it. But I encourage you guys to do the same. All right, what'd you think? Pretty straightforward stuff, not too bad? All right. Okay, so let's take a break here. And let's start back at 2 p.m. Okay, so it's 1:52 right now. I'll be right back at, we'll start literally right back at 2 o'clock. All right, so everybody enjoy a little bit of break, get up and stretch, and I'll be back in 8 minutes. All right, we're going to start back up in about a minute. Before we do, I'm just curious if people are interested, just saying in the chat, are you guys enjoying remote learning this semester, being at home? No. Some people are, some people aren't. I guess there's probably, I'd say it does. I live in New Jersey, so it saves me a lot of gas. I'm sure there's probably a big variation between how instructors are doing their courses, I would imagine. But I hope you're enjoying this class at least. Thank you. Thank you for that. You get an A. Everybody else C's. I'm just kidding. I'm just kidding. All right. Oh, thank you. Thank you very much. I appreciate that. I find the classes, I personally enjoy teaching remotely, but I do find you do miss a lot of the human-to-human contact, obviously. You do miss a little bit by being in person, but I don't get to tell as many jokes as I normally do remote, but anyways, let's finish up for the day. And so what I want to end class talking about is these measures of dispersion, okay? And dispersion is synonymous with the spread of data. okay? And so there's three measures of dispersion we're going to talk about. The range is the easiest one. And how many people, I'm just curious in chat, have heard of the range before? Maybe like an idea of it. Yeah. So the range is actually the easiest calculation we're going to do in class today. Then we're going to learn about these things called the variance and standard deviation. And these are two that are grouped together, and they're a little bit more complex, but they're also really important. And especially this concept of the standard deviation, we're going to talk about a lot in the coming weeks. All right. So measures of central tendency look at measuring like a typical observation. Okay, so now we want to look at how dispersed or spread out the data is. And what we want to do is we want to put a numerical measure to this. So numerical measure to the spread of data. Okay. So it helps answer questions like how typical is typical, and for most observations are close to the mean is typical, otherwise it's not. But let me first show you why we need to, with an example, and we're going to work with this data throughout the next 50 minutes of class or so, okay? Why we need this. So knowing why, or talking about why knowing the mean is not enough, okay? So suppose you have two samples, so notice that it's a sample, okay, of hourly wages. Now, I just made this data up, okay? So don't think that this is true at all. But I have hourly wages in South Dakota and some hourly wages in North Dakota. So I just called 5 people, okay, and I basically, in each state, and I just said, how much money do you make per hour? And these are what they told me. If you were to calculate the mean for both of these wages, okay, because it's a sample, it gets the X bar notation. You would add all these up and divide by 5. And in both cases, you would see that the average wage of this data set and the average wage of this data set is the same, it's 10. But look at the wages in South Dakota and look at the wages in North Dakota, okay? Is any data set, quote unquote, more spread out than the other one? It looks like there's a larger variation in the data set. Which wages seem more spread out? What do you guys think? Yeah, for sure South Dakota, right? Like these wages seem pretty clumped together, where these are more spread out. Okay, so this data is more spread out. Okay, so it's one thing to just say, hey, this data is more spread out, okay? What we want to now do is put a number to this, okay? And what you're going to notice when we start putting numbers to this, okay, for measures of dispersion, a larger value means the data is more spread out. Okay, so as we go through our measures of dispersion here, we're going to do them for both South Dakota and North Dakota. Every measure we get of dispersion should be larger for South Dakota compared to North Dakota. Okay, so these are the 3 that we're going to talk about. I'm going to do a little bit and talk about the strengths and weaknesses specifically of the range, and why maybe this easy one to calculate isn't the best one to use going forward. Okay, so the range. The range is so simple. It's just the highest value in a data set or max value in a data set subtracted the lowest value or the minimum value in a data set. Okay, that's it. It's just a super simple subtraction. Okay, so if you look back at the wages here, the max wage in South Dakota is 15, the minimum is 5, in North Dakota it's 12 and 9 correspondingly. So then the range of each, all right, the range in South Dakota is 15 minus 5 is $10 an hour. And the range in North Dakota is 12 minus 9 is $3 an hour. So look, the range is larger in South Dakota. I'm just going to put SD, okay, which is what we would expect because the data is more spread out. All right, expect this since data more spread out. right, that's it. I'm actually not even going to do another example of the range. It's just like the easiest value you calculate. You just take the highest value minus the lowest value, and that's it. Okay. All right, here are some advantages of the range or why we even bother calculating it. First off, obviously, it's easy to calculate, easy to understand. It's just the max deviation or max difference between the highest and lowest values. Here's some examples of how you might use it. All right, so one use of range is quality control, where absolute minimum may be needed to use to set for safety standards. So I always like this example to talk about. Suppose engineers are testing 5 airbags to see how long they take to inflate. And you don't have to answer this if you don't want to, but has anybody ever been in a car accident where your airbag has inflated? I have. It's super scary. And it was actually my fault too. You know, I was in the early 20s. We won't talk about it, but it's very scary. Anyways, suppose these are your results. Like these engineers test how long it takes to inflate, you know, 0.7 seconds, 0.8, 0.85, 0.95, 0.8. If you look at the range, just the difference between the max and highest value, you get 1/4 of a second. And if you've ever been in an accident like that, 1/4 of a second can mean the difference between life and death. So, you know, you got to work and decrease that range. All right, here's the disadvantage and why it's not commonly used in statistics. So why not commonly reported? When you look at large data sets, they may include what we call outliers, and we're going to more define outliers on next class. So these are unusual and extreme in value. So remember, what you want to do is you want to measure the spread of data. Okay, so get an idea of what the typical spread of data is. So if you look at the data set of income of US workers, the top income earner might be Bill Gates or Jeff Bezos or Elon Musk, someone like that. And the bottom earner might be a street vendor making $1 per hour. If you look at the range here, the difference between that, it doesn't tell us much, okay? It's not useful to describe the typical spread of data. It's just not a useful value because it's so large, okay? So we need a better measure of dispersion, okay? And to do that, we look at what's called the variance first, okay? And what the variance does, so measures of dispersion meant to describe how spread out the data is. So the variance is based on the deviation about the mean. So what the variance looks at is it looks at how the data deviates, okay, from the mean, from the average value. Okay, so it looks at, whenever we use the word deviation or deviates, okay, we look at their difference, or it's a little bit of a subtraction. So that's part of it. And just like the population and sample means, all right, we have a population and sample variance. Okay, so the notation is just a little different and very important here, okay? All right, so this is the population variance. It's given by this notation right here. So this is the Greek letter sigma, okay? So this is called sigma squared, okay? This is a population variance, okay? So this is a parameter because it comes from complete information. And then we denote at the sample variance, okay? This is just read as S squared, okay? And the sample variance is a statistic. Okay, these formulas look a little crazy, but they're actually not too bad at all. Okay, so I'm going to walk you through it. So when you have a population variance, the first thing I said was it's based upon the deviation from the mean. So you're going to take the first data value, x sub 1, and you're going to subtract away this thing called mu. Does anybody remember what mu stands for in statistics? It's a population what? It's the population mean, okay? So you're gonna take the X value, the first value in your data set, and you're gonna subtract away the mean, okay? That's gonna tell you how far the first data value is from the mean. And then you're gonna square it. I'll explain why you square it in a little bit. Then you're gonna add to it. You're gonna go to the second value in your data set, X sub 2, and you're gonna subtract away the mean. Then you're gonna square that. And you're gonna keep going until you get to the last value in your data set, X sub capital N. You're gonna subtract away the mean and you're gonna square it, okay? And then you're gonna divide by capital N, which is the population size. So in shorthand notation, this is what it is. It's the sum of each value of your data set subtracted from the mean, tells you the deviation of the mean squared, divide by N. So what the variance is telling us is it tells us the average deviation squared from the mean. Okay? And I'll explain like the squared in a second. All right, the sample variance, a little different, and there's this notation down here I want to talk about, but it's the same basic concept. You take the first data value, you subtract away X bar, and remember X bar here, that's the sample mean. And you add to it, you do that for the second value, you square it. Same thing, you square it. You get all the way to the last value, you see how far it away is from the mean, and you square it. So this is just the sum, again, of each data value subtracted from the mean squared. But there is a subtle difference that's incredibly important here. You'll notice here that instead of dividing by n, we divided by n minus 1. In statistics, this is what's called a degree of freedom. And we'll learn about that when we talk about what's called a t-distribution later on in class. But just in layman terms, what generally happens is when you take a sample, you're very unlikely to record all the unusual or extreme values away from the mean. So to correct for that, we just divide by n minus 1 because we recognize that our sum here is most likely to be smaller than it should be. So we just divide by 1 less. Okay, but just for now, okay, mean or the variance divide by n, population variance divide by n, sample variance divide by n minus 1. Okay, so why did I square all this stuff? Okay, squaring makes them all positive, okay, so to avoid any negative numbers. You'll see we're gonna do this by hand. If you don't square these values and you were to actually just sum up x1 minus mu plus x2 minus mu, they would actually sum to 0, which doesn't tell us anything, okay? So by squaring it makes the final answer really big. So unsquaring them, okay? To undo a square, you take a square root, right? Makes this what we call the standard deviation of a number much more useful, okay? So all I'm hinting at here is the standard deviation undoes the square, or it's just the square root of the variance. Okay, square root of the variance. So we just denote them as this, okay? There's a population standard deviation. It's just denoted as sigma because you square root the variance, you square root sigma squared. So it's literally just the square root of all this. The sample standard deviation is just denoted as S because it's the square root of S squared, and it's just the square root of the variance, okay? And what the standard deviation tells us is it tells us the average deviation from the mean of a data set. Okay, whew. Do these formulas look pretty crazy?
Professor, I just have a question.
Yeah, go ahead.
So I just want to like understand like the definition of the variance. So what exactly is it?
Okay. So imagine you have all these data values. Okay. Let me go back here. Let's look at South Dakota. Okay. And I'll answer your question in a second about do we need to remember them.
Mm-hmm.
This one right here. Okay. Wages in South Dakota. The average is 10, right? How far away is someone who makes $5 from 10? Like how many dollars per hour is it away?
5.
Okay, how far away is 7?
3.
And 11 is 1, and 12 is 2, and 15 is 5, right?
Mm-hmm.
Note, so we're difference of 5, difference of 3, difference of 1, difference of 2, of difference of 5. What is the average of that? That's what we're looking for here. So what the variance is it's the average deviation squared, okay? And what the variance, or what the standard deviation is, is just the average deviation. So it undoes the square. Okay, that's what we're trying to find here. Does that kind of make sense?
Yeah, it makes sense.
When we do this first example, it'll make a lot more sense. And then to answer the question, do you need to remember them? You do not need to remember any formulas in this class. Okay, when it comes to exam days, your exams are going to be open notes. Okay, because you'll be at home taking them. All right. That being said, even though this exam is open notes, I find that a lot of time, if you don't have done a little bit of prep before an exam, if you just like, oh, I'll just wing it and rely on my notes, you spend too much time going through your notes, and it screws you up on the exam a little bit. All right, so let's do this by hand, okay? And the first one we'll do by hand is South Dakota, okay? So this is what we saw. South Dakota is more spread out. Than North Dakota. Okay, that's what we saw when we were looking at the data. So should the variance and standard deviation be higher for South Dakota if it's more spread out? So remember, you're trying to put a numerical value to the measure of spread for data, okay? So a larger value means it's more spread out. So when we do this for South Dakota, yes, we should see that it's higher. Yes, it should be higher, okay? All right, I encourage you now, what we're gonna find is we're gonna find the variance and standard deviation for the South Dakota wages. Okay. All right, so the first thing you have to find, you always have to find the variance first. Okay. Does anybody remember if I said this was a sample set of data or a population set of data? Okay, thank you. Yeah, it's a sample set of data. So what you're gonna do is you're gonna go back and you have to find the variance first. So you're gonna need this formula right here, okay? This formula right here. So the variance formula is S squared and it's equal to the sum of each X value minus the mean squared divided by N minus 1. Okay, so just recall. Does anybody remember what I said the average wage was? I think it was, yeah, thank you. was $10 an hour. Okay, so if you're going to do this by hand, I use a table to help me do this. Okay, kind of like I did a table to help me with weighted mean. So the first thing in my table is I'm going to put X sub I. Okay, and what that is was that was the individual X values, the individual wages. So it was $5, $7, $11, $12, and $15. Okay. Now look at our formula here. The first thing the formula says to do is it says take each individual X value and subtract away the mean. Okay. So I'm going to take 5 minus 10. What's 5 minus 10? I got to be careful. It's not positive 5, but
Negative.
yeah, negative 5. So you have to be careful. So then you go to the next one, 7 minus 10. So remember, 10 was the sample mean here. That's minus 3. 11 minus 10 is 1. 12 minus 10 is 2. And 15 minus 10 is positive 5. Now this is exactly why we square it, okay? If you were to take minus 5 plus minus 3 plus 1 plus 2 plus 5, you would get 0, okay? So what we need to do now is if our formula tells us to square it. So I'm going to take all these values here and I'm going to square them. So I'm going to take minus 5 and square it. What's minus 5 squared get you? You get minus 5 times minus 5 gets me, yeah, positive 25. Yeah, I'm going to keep doing this. Minus 3 squared gets me 9. 1 squared gets me 1. 2 squared gets me 4. And 5 squared again here gets me 25. All right. What does this right here, this sign, this symbol right here, tell me to do again? I don't think you meant suck. That's okay. Yeah. That's funny. It's funny. Probably a Freudian slip, right? No, I'm just kidding. So what you're going to do is you're going to sum up this column here. If you were to sum these up here, I believe this would sum up to 50, 60. It would sum up to 64. Yeah. So this crazy part of the formula just becomes 64. Now we need to divide by something. Okay. N is the sample size. 1, 2, 3, 4, 5. So it'd be 5 minus 1 gets me 64 divided by 4. Does anybody know what 64 divided by 4 is? Yep. So what we just found the sample variance. And it's 16. Okay. Now it's very easy to find the sample standard deviation. We denoted that as S. Where does the 1 come from? That's just a formula. Whenever you're going to do the sample variance, you always take 1 less than N, okay? It's just a statistical reasoning behind it. Just for now, just take it as a given, okay? When we get to study the t-distribution and way after in a couple weeks, that'll make more sense. But for now, whenever you take a sample, just remember it's always N minus 1. Okay, yep. And so the standard deviation, exactly right. If you look back here, to find it, you just square root the variance that we just found. Does anyone know what the square root of 16 is? Yep. So that's it. So doing it by hand, now that the formulas do look a little crazy, but when you see it like this, me breaking it down, does it seem a little manageable? I got some really good news for everybody though. Let me ask you a question before that. Did while it was manageable, was doing it by hand kind of still not that fun? All right, I'll answer that. I don't think it was that fun. I got some good news though. 2 out of 10. That's about as high as I would rate it as well. Good news is your calculator will do this for you, okay? So everybody take out your calculator real quick, if you have it and you're following along, okay? I wanna show you to have your calculator will do this for you, okay? So going forward, you don't need to ever do this stuff by hand, okay? You can just have your calculator do it. So can everybody see my screen calculator here just fine? All right. Okay, good. All right, so this is stats class. So the button we're going to use the most if you want to follow along is you want to use this stat button right here. So everybody click the stat button on your calculator. What you'll see next up at top is you'll see 3 things. You'll see edit, calc, and tests, okay? We're gonna use calc a little bit. We're gonna use tests a bunch, but under number 1, edit, this is how you're gonna input data into your graphing calculator. So number 1 selected is edit. You wanna just hit enter right here. Just hit enter. And hopefully you should see this on your calculator. Does anybody not see L1 here on their calculator? Really needs to say L1 here. All right, everybody's good who's following along? All right, so what you're then gonna do is you're gonna take your data set, 5, 7, 11, 12, and 15, and you're gonna plug it in. So you're gonna press 5, you're gonna hit enter. 7, enter. Okay, now this is important. If you wanna clear out previous data, you go to the top L1 and do not hit delete, okay? You hit the clear button right here, clear, and then enter, and it will clear the data. So you scroll to the top, hit clear, then enter. So now you just go 5, enter, 7, 11, 12, and then 15, okay? So now you should have your data plugged in there. What you hit next is you hit the stat button again, okay? And now I want my calculator to do a calculation for me. So I'm gonna scroll over to calc. And I have one variable, okay? I had data on one variable on income. So I want this thing called 1-var stats right here, okay? So under 1-var stats, I'm gonna hit enter. Okay, now if you have a TI-83, this is important. You do not see this, okay? What you see on your calculator on your TI-83, I have no idea. To answer that question in the chat, I have no idea what calculator that is. So I can't help you on that. Okay, we were asked that you have the TI-83 or TI-84 for this. But if you can figure it out on your own, you can figure it out on your own. If you have a TI-83, it says 1-var stats, just hit enter on your calculator again. If you have a TI-84, you scroll down to calculate here, and you hit enter. Now, how many people see exactly what I have on my screen there? All right, good news, okay? First thing it tells you, X bar, the mean is 10. Wow, look at that. We said the average salary here was 10. If you scroll down, you'll notice it says something called S sub X and sigma sub X here. S sub X is the sample standard deviation, excuse me, and sigma sub X is the population standard deviation. So your calculator doesn't know if it's a if it's a sample set of data or a population set of data. So it just gives you both. And if you remember, we said the sample standard deviation was 4. Look at that, S sub x, 4, right there. Is it a lot easier doing this with your calculator? Oh my gosh, yes, right? Like doing it by hand, it took me 10 minutes to show you, walk through it. In calculator, it takes 30 seconds. Okay. Everybody's probably thinking, why didn't you just lead with that, Matt? But it's just, it's good to know how to do this stuff by hand, you know, just so you understand the workings of it. Okay, you'll notice the TI-83. I'll just show you real quick on the TI-83. So hopefully you can see the TI-83 right here. You're just gonna hit stat. Under number 1, you're gonna edit the list. You're gonna type the data in. So then when you press the stat button again, under calc, it's the same option, number 1. The only difference here is it says it's asking you, do you want 1 var stats? And then you just hit enter again. And you can see it's the same stuff here. Okay. Does that help, Paulina? All right. So the only time, so just again, real quick, whenever the options that you press are basically the same, I'm just going to show the TI-84. There is a few examples later on in class where there's a slight difference between the TI-83 and TI-84. I will show them both in that case. But when I only show up the TI-84, just means it's roughly the same. Okay, great news. Just because of timing right now, I will leave you on your own. For homework, you can just write the calculator. To answer that question. Generally on homeworks and exams, I'll talk about that. Let me go back to that. To answer your question, where's the sample variance? If you take, the calculator doesn't directly give it to you, but to get the standard deviation, you square root the variance. So if you have the standard deviation, how can you get the variance? Can anybody guess? Well, you did, yeah, exactly. So look, here's 4. If you square 4, you get 16, which is the variance. So when you have the standard deviation, you can square it to get the variance. That's a fantastic question because I always ask that on an exam. So now you know, to get the variance, you square the standard deviation. To go back, you don't have to do anything by hand, okay? For this type of simple stuff, you'll ask, you can use your calculator. When we get to the harder stuff to use your calculator, I'll ask you to write on the exam what you put into your calculator. That'll make more sense when we get to that section. But whenever I show you how to use your calculator, you can use that for homeworks and exams, okay? All right. I'll leave you on your own. You can try getting S squared and S for North Dakota. Or what did we just do? Yeah, South Dakota. For North Dakota. All right, when you do, you'll get S's roughly when you round it, 1.17, okay, for North Dakota. That's, you can practice on your own for your calculator here, okay? So this is what, going back, this is what we saw here. You're gonna see here, S squared here is 16 and S is 4. If you do North Dakota by hand, you'll end up getting S squared as being equal to 1.375. and S ends up being, when you round it, 1.17. So this data is more spread out, and we're seeing that, okay, when you calculate or compare these two values, okay? So I just want to put another visualization to this. All right, here's two different data sets here. Okay, I just made these up from somewhere. Here's data set 1. Here's data set 2. If you look at the values, all right, what you're seeing here is data set 2 is more spread out. Okay, like if you look at these values, they're kind of clumped together, whereas this one goes all the way from 20 to 70. And if you were to calculate the mean of both data sets, the mean would be the same, but their standard deviations, and this is also another good way to practice your calculator if you want. You can plug these two data sets in your calculator and see that data set 2 standard deviation is like twice as high almost, okay? And you can see the spread of these two data sets when you look at the dot plots, okay? Here's data set 1, and here's data set 2. Right here, the data is pretty clumped together by the mean, and here the data is way more spread out. Okay, and so this data set's going to have a larger standard deviation, and we see that. Okay, in the data set here, the number's just higher. Okay, so just remember, I'm just trying to hit this home. Larger values of S squared and S, this variance and standard deviation means the data is more spread out. Okay. All right, so I want to end class talking about the empirical rule, okay? So larger standard deviations means the data is more spread out. But what does it mean, or is there any practical application for something when you say what the standard deviation is 1.17 or the standard deviation is 4? So like, how can we use these values? Is there any practical use for these, okay? And you can using what's called the empirical rule. All right. And this works whenever you have quantitative data that's roughly a bell-shaped distribution. So whenever data is approximately normally distributed. Okay, so whenever your data looks like that bell curve, like this, okay, this empirical rule will hold, and it's really a cool property. So there's 3 unique properties to it. Okay, it turns out that if it's roughly bell-shaped, approximately 68% of your observations will lie within 1 standard deviation on each side. So if you take the mean and subtract a standard deviation, and you take a mean and add a standard deviation to it, between these values, 68% of observations will fall. Property 2, if you go further, you subtract another standard deviation and add another standard deviation. So X bar minus 2 standard deviations all the way to X bar plus 2 standard deviations. 95% of data will fall. And then you can even go one more. If you go 3 standard deviations away from the data, from the mean, you get 99.7% of observations, okay? And this is what you're seeing when you look at this, okay? Here's the mean of a data set. Okay, like let's just put some numbers to it, okay? Let's just say X bar was 50 and S was 10. Okay, I'm just making this up. So here's 50. If you subtract a standard deviation, you get 40. If you add a standard deviation, you get 60. So what we're able to say then is 68% of observations fall between 40 and 60. If you go another standard deviation, so subtract another 10 away, you get 30. add another standard deviation, you get 70. You're able to say that 95% of data falls between 30 and 70. If you go even further, 3 standard deviations, so subtract another standard deviation, you get 20. Add another standard deviation up here, you get 80. You're able to say that 99.7% of observations fall between 20 and 80. And that's just a great use of the standard deviation. We'll actually use this property a lot. When we get to statistical inference. Okay. And it'll be how we determine if things are statistically significant or not. So we'll get a chance to practice this a little bit more in the coming weeks, okay? But here's just another quick example of this using some of the values that we got from the North Dakota, right? So the mean was 10, the standard deviation was 1.17, okay? If you take and subtract the 1 standard deviation on each side, you'll get 8.83. If you add 1 standard deviation, you'll get 11.17. And you just be able to say something like 68% of observations fall between those two numbers. Okay. All right, I know that was quick, class, but I'm actually going to stop the lecture here. Does anybody have any last minute questions for me? Yeah, go ahead with your question. If you had one.
I would like to go to your office hours and talk about like the homework and stuff because you know this is my first day.
Oh, did you miss last class?
Remember, Professor, I told you. Yeah, remember I told you that my job had me through schedule. Like my schedule was like collab between this class, and then my job finally got my schedule intact, so I could be able to be in class now.
Yes, I do remember now. Why don't we end class and why don't you and I stick around and we'll talk for a little bit because you missed my office hours this morning. Okay, so we'll talk after class. Okay.
Okay. I'm actually getting ready to work right now too, so yeah, that's like I start working at 4.
All right, let me actually just stop the recording real quick.
Okay.